Welcome to the sixth lecture on random processes. Um, we have been working on defining random events, random variables, and random processes, yeah, from scratch. And in that, we went on to talk about assigning probabilities, or let's say the functions that typically hold the probabilities that we assign to random variables, right? And so far we've been working with single variable, and within that, so um, if you remember, this is where we started, yes, and t was then in, we wanted to have discrete versus continuous, and states here were also discrete versus continuous. This was, we won't go into this now anymore, as you remember, and even we weren't going into this, yeah, we were just working with the single random variable, and within that we had defined the from the size of this or the nature of that, yeah. So continuous for us was uncountably infinite, yes, and discrete for us was either finite or countably infinite, yeah. And the last, sorry, countably infinite, yeah. So the last whole lecture had been about distributions, or what kind of functions we use to summarize or collect the um, probabilities of these guys. So from all of this we were over here, yeah, and today we will go here and maybe little bit beyond to, from one variable to two, and two to many, yeah. So we'll see if we have time for the last part, but we will, that is the plan. So what did we discuss here in the how we collect the probabilities or assign the probability? What functions did we discuss?
Probability distribution.
Right. So we discussed the probability distribution. Sometimes we already did probability distribution function. What else? Probability.
Cumulative.
Before that there was some mass function, right? And then there was the cumulative distribution function, yeah. So probability, what was the difference between these two? So in probability distribute, all of these we discussed for the discrete case, that was one thing, yeah. Secondly, the probability distribution was defined only on the values, right, where this exists. So if you're rolling a die, then your possible values are x1, x2, x6, which are 1, 2, 3, 4, 5, 6. So probability distribution function basically defines it at xi equals, defined as probability x equals xi. To emphasize that this is for x, we put capital X here, yeah. And given that xi's are from this set, this was probability distribution. Whereas for probability mass function, right, what did we do there? Basically we said, okay, probability x on any x. Here x, let's say if I move this guy here, and I can say x equals x, and x could take only values in x1, x2 and x6, yeah. Whereas here x could take values in real numbers, any number, yeah. And we said this is x equals x, but then we said that x for us, although it can take any numbers, but for x not in this set, x1 and x6, the probability will be 0, yeah. Or this assigned, we know the probability is 0, but the function's value will also be 0, yeah. So it's a subtle difference, not huge, but it's good to know. Then the main thing here, from here we go to, what's the main difference when we go from PD or PMF to CDF?
CDF is a summation of previous ones, previous math function.
Yeah, summation is mathematical, but what's the key conceptual difference? So we are going from point to interval, right? That is the conceptual. The natural consequence of that being summation, integration is secondary. Yeah, but conceptually, here you're talking about equal. Is x equal to this value or not? Point. Yeah. Then you jump to range. Is x in this range or not? And that we defined as the cumulative distribution function. For this case, it came out to be the summation. Yeah. But so what was the cumulative distribution function? What symbol were we using? Capital F?
Capital F.
Capital F.
Okay. So then um, capital Fx of x was defined as the probability. Yes. What? X is.
Not equal to.
We don't define the left side because it's up to that. So the interval is minus infinity to x. Yes. And if this happens to be a discrete case, then it becomes a summation, right, as you say. We'll see today that for continuous case the definition will be same, but instead of this coming into a summation of the probability mass function, it will be integral of the PDF, probability density function. Yeah, otherwise it's not different. Did we discuss what properties did these guys have? These two, they have to satisfy Kolmogorov's axiom because they are probability. Whereas this is not probability in the sense that this is not probability at a point. It's a collection of probability, but it still had some some values, right? So what were those or some properties? So fx
A greater than or equal to 0.
yeah. So and then minus fx minus infinity was 0. Fx infinity was
1.
1, right? So it has to cover the total sum or total area, depending on whatever you're looking at. It should be 1. And as we saw, the continuous case, if a is greater than or b is greater than a, yes, then
F of
fx b must be
minus
greater or equal to fx a, which you can write as
Okay.
minus
Minus.
a should be greater or equal to 0. Yeah. So this we saw that it tells us that fx is always a non-decreasing function. Yes. So then we also saw some interesting results that fx min and fx max, what was their value? Basically the at the minimum value in its range and the maximum allowed value. So we saw all that in detail. Just wanted to summarize quickly here. Let's see where we stopped. Yeah, we basically stopped here where we talked about fx being a yeah, and of course at any given point it has to be
greater than
non-negative. Yeah. Okay. But where is the condition that it cannot be greater than 1? Does it have to satisfy that?
Greater than 1, no.
yes.
We
sir.
didn't write that. Yeah. But is that included here? Actually, that would be redundant. It seems it is here. Where do you see it?
I didn't understand the question, sir.
So we normally in Kolmogorov's we say that probability of x less or equal to 1. Yes, cannot be greater than 1. Here we didn't put any such condition on CDF. Yes, but do you think that condition should apply to it?
If the function is convergent to 1, then you will type.
That
Yes, sir. This condition should be there.
it should apply, yeah. But with what we have already defined, do we need it?
No, we have defined the fourth one condition that I think that
Which one?
the fourth condition,
one?
yeah, and the third condition that will mix up together will satisfy this one.
Yeah. So essentially we already said that the total sum it can have or the total area it can have is 1.
One.
So we are saying this without actually saying it, but we actually know that it is less or equal to 1. Yeah. So because of this, that's why we're not rewriting it separately. But of course it has to be less or equal to 1. So today we go now in this branch. Okay, there are similarities and there are some differences. Yeah, and the very nature of the continuous introduces some very interesting, sometimes a bit counterintuitive things also, right? Because that's how the continuous, the differentiation. There are some things that involve infinitesimals, they involve infinities, they involve, and that sometimes looks a bit counterintuitive and interesting results compared to discrete case. But for most part, the main difference for most part is going to be that summations will be replaced by integrals, areas will replace the total sum for most practical purposes. But let's formally go into it and also define or discuss some of the interesting offshoots. Yeah, but in practical applications we're not too concerned with those. Right, now for a continuous random variable, it does not make sense to talk about here, remember, point and interval, probabilities at a point and probabilities in intervals. For continuous random variable, it does not make sense to talk about probability at a point. Okay, I will come back to that. But what does make sense is talking about probabilities in ranges. Okay, so we will discuss this in more detail, but let me just first write this thing. So we could so let's say we want to find if a continuous random variables lies in the range, let's say b a, where b is greater, a b, so where b is greater than a, let's say. Yeah, so in that case what we are looking at is probability that x is, let's say, greater than a, less or equal to b. We have to leave one of them open usually because of the continuous issue. We'll see that, but let's see this thing. What can it be in terms of the cumulative distribution or density function? Yeah, so you can see that this should be fxb minus fxa. Yeah, so for continuous cases it makes sense to say, okay, what is for a continuous case, why doesn't it make sense to talk about probability of a point at given point, even if it is a uniform continuous distribution in say 0 to 1, all points have, let's say, are equally probable, it's uniform distribution at any given point, one point, because there are infinite number of points here. Yeah, so the probability of each one will approach 0. So what's the probability that it is 1? Well, it's basically 0 because there are so many candidates. There is 1, 1.000001, right, and so on. But you can ask, okay, what is the probability that this is in the range 0.999999 and 1, for example. You could ask that question. Yeah, but since there are infinite number of points here, assigning individual probabilities becomes problematic. So let's first come back to this thing. Okay, ranges are possible. What we can do, well, then what will happen to we had the probability distribution or mass function for discrete case, which had probability x equals x. So what's the equivalent of that then? Can we have a direct equivalent of that or a proxy of that? Yeah, we cannot have an exact equivalent of that exact point, but we can have a proxy. Proxy means something that will, for all practical purposes, that will help us answer the same questions that probability distribution helps us do in discrete case, right? And that you know is the probability density function. But where does it come from and how is it exactly different from our, so what I'm talking about here, we had the probability mass function for discrete case, right? What is its for, and we also had the cumulative. Cumulative is fine, right? Because there it was on ranges, here also it works on ranges, so it's fine, no issues. What about this guy? What is the continuous counterpart of this guy then? Because it says probability x equals x. For continuous x equals x doesn't make sense. Yeah. So what is the conceptual counterpart of this guy that can help us? The proxy of this guy. Yeah. And that is going to be the PDF, small d, meaning probability density function. So let's look at that. Now we can talk about probability in a range, okay, for continuous cases also. What if I make this interval much smaller? I can do that, right? So I can make it as, let's say, delta, with the delta very small. Yes, I can talk about very small range. Then what is I'm looking for is probability x is between this thing, yeah, which is a very small interval. Yeah. Okay. So then what is it in terms of cumulative? Right? Now you can already start seeing this seems a lot like when you first develop basics of calculus, differential, yeah, from differences to differential. In fact, it can be continued exactly in the same way to conclude that if the derivative of fx exists, we can give it a name. So you can keep making it smaller and smaller and start getting smaller ranges, and then apply the idea of infinitesimally small things to eventually get to something which you can call as the derivative of fx with dx. This derivative we will give a name. Okay, what's that name? That name is the proxy for the continuous case, and we call it the PDF, represented as fx x. Okay. What is the assumption here for this guy to exist? That fx is
Derivative must exist.
differential. Okay, so that is the condition. Now when you hear such a thing, always ask yourselves, okay, are there situations where it's not differentiable? Whenever you hear assumptions, attack the assumptions, because there you can find or learn new things. Yeah. So I leave that as a homework for you to look into situations. Yes, there are situations where fx is not differentiable. Okay, particularly situations where fx is not differentiable at some points. What happens then? In most cases, you can still assign this thing. Okay, but I leave you as a homework to see what's the approach.
This differential, the derivative of that function cumulative will work on the both cases, countably infinite and countably infinite.
This is for the this is for the continuous case, uncountably infinite. The other case is discrete. Derivatives don't apply to discrete
Then
cases.
you put a question mark here. Then how we'll find in the same way the probability mass function at this specific point? Suppose that we have a rational number of sets, and how we will specify same rule will apply as real number कि हम रियल नंबर में जिस तरह हमारे पास होता है कि हम कोई भी पॉइंट सेलेक्ट कर रहे हैं कितना सेलेक्ट करेंगे इसी तरह हम रैशनल नंबर में भी तो कर सकते
As long as this your set is continuous, right? The same thing will hold. Yeah. So yes, it's the same issue. Yeah. There's when you're back to countably infinite or finite, which is the discrete case. Yeah. There it's different. All you have to distinguish is my case continuous or discrete, and within discrete there are two cases, within continuous there is just one case as we discussed. Yeah. So take any set, rational or any other set you want to take, ask yourself, is this continuous or not? If it is, then you are talking about the continuous case, and in that case you will use this approach, that you will use the probability density function, which will be the derivative of this thing. But now this is a mathematical thing. It makes some sense. What it's saying is you are making this thing smaller and smaller until you reach one infinitesimally small point, which what you do in derivatives. But there are what is the meaning of this then from probability point of view? Yeah. So you could say, just imagining from here, this is the probability of the variable line in infinitesimally small interval around x, right? That's one way of looking at it. But you could also say, okay, it's basically for our case, whereas this was saying probability x equals x, this guy is not exactly saying that. It is saying we like to name it as the relative likelihood. Okay, it's the relative likelihood of this value showing up. Okay, so I'll give you some examples to make that clearer. But keep in mind, whereas this is saying probability x equals x, exactly. This is never saying. So if you find that at a given 0.5 it's half, don't think I'm saying that x equals 0.5 is half. Okay, it's the relative likelihood of this thing happening. We will see some examples here to bring home that point. But now let's look at it as like this one also. Then can I write this thing, rewrite it, I guess, like this: fx dx is dfx x, yeah. And this thing for us, now this thing is basically probability, as I said, x between x and n infinitesimally small increase, yeah. So in infinitesimally small interval around or starting from x. That was the mathematical thing. Now this is going to be used and it is going to help us find the probabilities in ranges also. Yeah, we can use it to do that. We can see how do you go back from fx to, if you have PDF and you want to get the range now, how do you go back? Integration. Yeah. So what would be the integration? Can you write? I'll give you a few moments to think about it, and then let's see. I want to write fx x in terms of the small fx. Yeah. So it's integration. Yes.
to b there must be range
from x to the
So what should it be? Let us see. It is f x. This you have to tell me now. What are the ranges?
from x to x delta x.
minus infinity to infinity.
वो तो इधर था ना? I'm not talking about dfx.
Yeah.
I'm talking about fx now. So minus infinity to.
Yes.
ये तो आपको पता है ना? इसको think of it in probability. In probability, it was saying what is the probability that x is between minus infinity to x.
Yes.
That was the definition. If you think of it, before it ended up in summations, Yes, now it will end up in integration, but it will start from here to where? Small x.
Yeah.
Yeah, this guy.
Yes.
Now you can't use it here anymore. So you need a dummy variable. So let's call it u, then du. Yeah. So that is of course the natural definition of say the cumulative in terms of the PDF. So that of course what happens if we want this to be between A and B in a certain range. So let's say I want probability. This is a special case. It's minus infinity to x. Yeah. But what if I wanted the probability that x is between A and B from PDF? So what would it be? In terms of CDF, you know, it's f capital Fx b minus capital Fx a. That you know. But in terms of that guy, what would it be?
The limits will be changed from A to.
Yes, that's all. Yeah. So it's the area under. So now you can use x if you want, because it's not being used here in the limits.
Same like fundamental theorem calculus.
Yeah, from doing the opposite of derivative. Yeah. Okay. So let's see what else we have here for you. So the ranges are fine. Let's talk about some properties of fx, this PDF. Yeah. So what are the properties? Let's see. Can you think of any properties we should assign to this guy fx, small fx?
Yes, same property. I guess it's a probability, the same property. I guess this will apply. It's greater than equal to 0.
So it should always be greater or equal to 0. Fine. Why?
Because it's probability.
No, it's not. That's the thing. In case of this px, yeah, it was right. Here we have no such definition, right? So here, yes, you had it. By virtue of this being greater or equal to 0, you had to say that this is greater than. Here I don't have that.
It's change in a cumulative distribution function. That's why it's a positive.
Okay, why is the change positive or 0?
It is a non-decreasing function.
No, and that's why we discussed it. Yeah. So already knowing the properties of things, sometimes they seem trivial. Okay, why are we talking about CTF being non-decreasing? But see, already they start helping us in more analysis. Yeah. So this is the derivative of a function which we know is non-decreasing. So the derivative, the slope will either at some points be 0, at others it will be positive, non-decreasing. Yeah. So yeah. So although we ended up with something similar, the reason was different here. Yeah. Okay. So then what else? What should be the total area under the PDF?
Minus infinity to infinity of x is going to be 1.
Yes. Should be 1. Since why is that? Because this is representing the probability x is from minus infinity to infinity. Now where else would it be? कहीं उसी में होना है ना, अगर सही फंक्शन आपका है. Right. So I guess that is that makes sense. Now let's see an example which will also help us see why it is not the probability, it's density. Yeah, it's not the exact probability. For discrete time cases, we had, let's say, 1 by 6 for 3 points. Yeah, they were exact probabilities. Here, for the continuous case, whenever you're drawing the probability, whatever shape it has, firstly, if you see any part of it going down here, something is wrong. Yeah, not allowed. And if you find its total area being, we're not saying it has to be less than 1, it has to be exactly 1. Yeah, if you find its area more or less than 1, something is missing. Yes, so it has to be 1. Okay. Now, but other than that, what does, in this case, this also had to satisfy these things. You couldn't go in negative. The total sum had to be 1. Yes, but other than that, we knew what each value meant. It was probability x equals 1, probability x equals 2, so on. Here, what does this each value mean? Yeah, it's like we will see that. Yeah, it makes sense, and mathematically it's spread out over a continuous thing. That's why we call it density. Remember, फर्क है ना density और distribution you can do discretely. Distribution, density is spreading out over something continuous. Yeah, so you have spread out this thing over something continuous, and in a way that it still follows some logical conclusions based on our understanding of what it is supposed to represent as a whole. Yeah, so let's see an example. You remember the uniform distribution we talked about? So uniform distribution is when every point in the range has equal probability, equally probable. For discrete case, one very simple example is you're rolling a die. 6 possible outcomes, each one has probability 1 by 6. Yeah. So, and we said that this interesting definite lottery that for countably infinite uniform is not possible. Okay, at least that's how we understand it. Now for continuous cases, uniform is very common, and we often write it as, this is the symbol we often use to represent distributed as. Okay, so x is distributed as a uniform distribution. Okay, and what do we need to define for uniform distribution? याद है basic courses से. What parameters do we need to define a uniform distribution completely? Interval, that's all you need. Yeah, actual value नहीं चाहिए होती. We will see why that is. Yeah, as soon as you define the interval and you say it's uniform, you can get कैसे वो area 1 करना है ना तो
1 over
yeah. So let's say I define it in like this. It's in 0 to 1. Let's say. Okay. So then I'm talking about something that is uniformly distributed in this range. Now, it is logical to say that any value here, since we're saying it's uniformly distributed in this range 0 to 1, what is the probability of any given point? I don't know, or it's 0 because there are so many points. Yeah, I have to spread it among. But I do know this. If I'm saying it's uniformly distributed, it has to be a straight line. Yeah. So this will help you understand the difference between saying probability at this point is this point is. I didn't start with that. I didn't say that the probability at every point is equal and this is the value, because at any given point the probability is 0. Yeah. What I said was, okay, I know whatever it is, it has to be equal. Yeah, this is the density function, and now I know if it is to be the density function, I know this density function has to meet certain criteria. It meets the first important criterion, it's not negative. Nowhere it is negative. What was the second one? The total area had to be 1. So without now knowing what is this here, yeah, beforehand, I can, let's say, put an alpha here. So what is alpha?
1 over b minus a.
Yeah, so in this case क्या होगा?
1.
Alpha is
1.
1. Yeah, makes sense. तो ये drawing थोड़ी खराब हो गई. Square बन रहा है. Yeah. So it is 1 times 1 is 1. How did you reach that conclusion? You know that the total area had to be 1. So alpha, I conclude, is 1. Now in discrete case, if you had put alpha equal to 1, you would be saying that each point has probability 1. Yeah, but here that 1, what does it mean now? I'm trying to bring home this understanding that conceptually density or a value of density does not represent the probability of a given point. What is it saying? अब इसका क्या मतलब है? Alpha equals 1 alone has no meaning for us actually. Okay, where does the meaning come from? When you see what's happening to its left, right, everywhere else. Yeah, alpha equals 1, so fx. Now what is fx x 0.5?
1.
1. What is fx 0.6? 1. Am I saying the probability of showing or getting 0.5 exactly is 1?
No.
In discrete case I would be saying that.
Yes.
Here what am I saying then? Alone it means nothing. It's relative to, okay, they are both equally probable. Yeah, then I'm saying, okay, this, what I'm basically saying, likelihoods, it's a relative likelihood. That's the part. Relative, you know what it is. Yeah, relative likelihood measure, kind of. Okay, आप कहते हैं, अच्छा, I don't know what height that is, but let's say if that was this much, then how much would you want? Yeah, arbitrary एक reference set कर लेते हैं आप, you set an arbitrary reference and then you assign probabilities to the other part. Let's say there was something that was not uniformly distributed but had, let's say, some distribution that went like this. Just for the sake of argument, I'm just going to write here, let's say 0.5, and this value I'm going to say 1. Okay, let's say there is some distribution. As long as it covers, I'm not assigning these and not the actual, as long as this thing is 1. Yeah, then what would it mean? Let's say this is at 0.5. So probability or the fx at 0.3 is, let's say, 0.5. This means nothing. Alone it means nothing. But then if I compare it to, let's say, at 0.7, I might be getting 1. So I'm saying 0.7 is twice as likely as 0.3. This is relative likelihood. समझ आ रही? थोड़ा सा absorb करना पड़ेगा आपको. It's easy to leave this part. You know, we could just do the math.
But
It's fine.
the whole area is actually the cumulative distribution function.
Yeah.
We are here talking about the derivative of that cumulative distribution function. So we are saying that the probability that is coming from a, let's suppose the previous one example fx of 0.5, 0.6, we are saying that is not their actual probability, that just values shows that they are equally probable.
Yeah, in its interpretation, it's showing us that what is, if we are saying that fx 0.5 in this case, fx 0.5 equals 1. If we are saying it doesn't mean that probability x equals 0.5 is 1, then what does this 1 really mean? Yeah, so it's like this. You have distributed or assigned probabilities to points, okay, in a way that together their probabilities together is 1. Then everybody gets according to its own likelihood, right? So it makes sense. This 1 alone is not saying anything. In discrete case it says probability x u like. In continuous case it's only helping us see, okay, which parts are more likely, how much more likely, and which parts are less likely and how little likely. Yeah, so in this case, of course, we see that alpha is 1, and let me see if we have, yeah, so with that, now with that you can work with the ranges here. Yeah, so let me give you an example. Now if you know, if you have assigned this alpha equals 1, you have defined the likelihood, and what is the probability that x, let's say, is less or equal to 0.5? क्या है probability?
1
0.5.
0.5, yes, half, आधी होगी ना. Even without doing the maths, you should be able to see uniform है. Yeah, the chances that you fall in the left part of the interval should be equal to the chances that you fall in the right half of the interval. Half आएगी. Yeah, mathematically, what is this? Is this f(x) 0.5 or not? है नहीं? Okay. What did we say? How was this related to density function? क्या किया था हमने जब दो इंटरवल थे? Minus infinity, of course not mentioned here, but that's what we thought. Minus infinity to 0.5 fx. This is the area under this guy from here to here. And when you do it exactly mathematically also, area under this function from 0 to 0.5, it will represent the probability in this range. Yeah? So at a given point it is the relative likelihood. In ranges, yes, it is the CDF. Okay, so it kind of helps us still work with CDF, still work with other things we will see later, the moments, the mean, the variance, all things that you could derive from the PXX thing, this thing, the probability mass function for discrete case, whatever you could derive, you could sum these up to get the CDF. Now you can integrate this guy to get the CDF again. Yeah. Later we will see for discrete cases you can work with this to get mean, variance, kurtosis, other moments. Yeah. Similarly, you will be able to work with this to extract those information. The only thing not identical is that what happens, what is the definition here, what is it saying? Well, this guy is saying something very simple. This guy is, if you see fx equal to 0.5 is 1, this is basically the derivative of the cumulative function at that point. In mathematical terms. In let's say conceptual terms, it is alone, it doesn't mean much to us. It is in relation to other points or regions that it makes some sense to us. Okay, so that is something I wanted to cover here. Let's see. Can you find the cumulative? Let's you can try on your sheets for a moment. What can you find for this example? Can you find fx and plot it? थोड़ा सा try करें जल्दी से, then I will see. So you're looking for the CDF of a uniform distribution over the interval 0 to 1. Yeah. There are many approaches you can use. I'm fine with whatever you use. I just want to see if you conclude something here.
It's going to be 1, sir. Area 1 area 1
This is going to, you have to plot it as a function of x. So this is x here,
okay.
and you have fxx here. So plot now capital Fx as a function of x. If you have derived it somehow, whatever, what do you get? Interesting.
That is kind of a relation where we mapping an interval to as a one point actually.
Mm-hmm.
So quite different.
To 1 point, why 1 point?
So one point is the area f of x, whereas its area is one. The one point integration.
The area is the total thing, yeah?
Yes, sir.
But I think you're confusing the area under capital Fx.
Yes.
We never said it has to be 1. Yeah, we said capital Fx at infinity has to be 1. Right? Okay, ask yourself this question. Let's start with, there are many ways of doing it. Yeah, let's do it more mathematically at first. Yeah. How is fx, the small fx which you have now, and you want to find this? Yeah. Do you know any equation or relation where you have this guy on the left and this guy on the right?
Yes, sir. Differentially, the differential one, the
Yeah.
derivative of cumulative will give us the f of x.
Okay, that's one thing. So we said it is dfx by dx. Yeah. Okay. What about the other way?
Integration.
Was this also
Yes, sir.
the case? Yeah. So can you use any of them to go from here to plotting this guy? दोनों use हो सकते हैं. Yeah. But maybe try with this one.
The
How
area,
how would you apply this?
the area between 0 and 1 is going the
So you're going to the extreme now. You have to find the function as function of x. So let's say we pick some x here. Yeah. Yeah, we pick some x here.
the head. Permit to recording individually now.
G. So at this point the capital Fx should be what?
Uniform arithmetic x.
इस फॉर्मूले से बताएं.
नहीं area under the
Area under this guy
Yes,
from
sir.
here to here.
yeah.
कोई वैल्यू होगी. 0 तो नहीं लग रहा. Yeah. Okay. What about here? What is the value here? Area under this guy. भाड़ा कम हो रहा है.
बढ़ रहा है.
बढ़ रहा है. बढ़ रहा है. बढ़ रहा है. कहीं जाके फिर वो रुक जाएगा. Yeah. And before that there is area under it is 0. It, you can check also in many other ways, but it will come out to be, this is increment is कोई there is no bigger or smaller increment. Yeah, increment is steady. Steady है कि नहीं?
Yes.
इसकी slope तो fix रहेगी. Yeah, it will have a fixed slope. After this point, increment will stop. Slope will become 0. Before this point, no increments happening. Minus infinity to here 0, minus infinity to here 0. It's only at this point that it starts accumulating area, and it accumulates area at a constant rate. Right? क्यों? क्योंकि this is a constant, yeah? Accumulate area at a constant rate, then it becomes this thing. Now look at it from this guy's perspective.
That is change.
Aren't we saying this is the rate of change, the slope? Look at now. Notice here fx. Before this, what is fx? 0. Yeah. Over here, within this range, what is the derivative of fx? Some fixed value, which we actually found to be alpha. So it's a fixed value. It means it's going with a constant slope. After that, the slope becomes, what happens? The slope further becomes 0. So it becomes constant.
Actually, we are always getting confused by considering that small f of x is the probability. We always getting confused that it's a probability of function.
Okay. But once you see it, it's very simple, isn't it? Both ways, from area perspective or rate of change perspective, it's very simple. Yeah. Okay. So let's summarize quickly, and then we will do from 1 to 2 random variables next time. Yeah. I may have to go earlier. Yeah. I'm going to do a quick summary of what we have done. We have assigned PDFs to continuous random variables. Yeah. For the case of the discrete, we had already done that, which was the probability mass function. Here we have assigned the density function. Cumulative can always be derived from here. Yeah. So if the derivative exists in this case. Okay. For this was continuous case, this was discrete case. And as I said, it is important. Why do we want to go for this? Actually, these functions, once you have them, like for the discrete, for the continuous case, we had the uniform case like this. Yeah, 0 to 1, alpha 0 to 1. You have effect. Once you have it for a random variable, there is a lot you can extract from it. Very basic one being, you can find, okay, what is the probability that it lies in a certain range. Yeah. In case of discrete, you can also find what is the probability that it lies at a certain point. Here you can only tell, okay, what are the relative likelihoods of certain points. Yeah. Okay, that's one thing, but we haven't gone beyond that. Next next lectures, not the exactly next one, but after that probably we will go beyond that and try to extract other information out of it. Can you think of what kind of information usually we extract from density functions and distribution functions?
The continuity and differentiability we have discussed.
From in terms of probability or randomness, expected value,
Expected value,
variance. So moments. Yeah. So all of those are defined actually in terms of this and this. Yeah, moment generating functions defined in terms of these guys. So it's not a simple curiosity to have this. So I want to spend some time developing this. I could simply tell you, okay, this is PDF, density function, this is density function, and then stop it. But you know, it's good to have your basics very clear. Up clear ho gaye? There is a lot going on in the jump. In jumping from here to here, a lot happens conceptually. Okay, you have to be clear on that, what happens. So What is the information we can extract? As I said, I will write it very briefly. We will come back to most of this later, but just to give you a quick teaser trailer for the what are the different informations we can extract. So for the continuous case, let's see if it's distributed like that. For the continuous case, कौन सी distribution लग रही है? Which one? Normal, huh? Gaussian.
Normal Gaussian.
Gaussian curve. It looks like that. Yeah.
Welcome.
Let's say there is an A here. Then you can find probability x is less or equal to A as f minus infinity to infinity fx A x dx. Yeah. So you can extract this information from this guy. Yeah, as I already mentioned. You can also extract information that it lies in a range. Let's say some range A to B. What is that probability? Okay, then that is even A is greater than B is greater than B. Yeah? Otherwise, it will become mathematically impossible. So there is A to B fxx dx. What else can you extract? The expected value, first moment, yeah, the mean. What is that? किसी को याद है? No, for any PDF. ये तो मैंने ऐसे draw किया हो just to show कि this is the area.
Yes, f of x f of x dx.
Yeah. Suddenly in this formula something else has shown up. We will see that in great detail later. Yeah. But what I want you to tell you here is to find this. If you know fx, the PDF, see, you can find this, you can find this, you can find this, you can similarly find variance. In fact, you can find the nth, let's say, distribution, yeah, of this thing. Sorry, nth moment of this thing. I won't write all the formulas. You know, for variance, it's x minus mean squared times this thing. Yeah. So same thing you can do for the discrete case with the help of what? The probability mass function, yeah, which is then summation. It is, let's say, x is minus infinity to a. We know that x is discrete, so it will be only having some value there. Rest will be zero automatically, and this is, you can find that. Similarly, a and b, what will happen? X equals a to b, yeah, for that. For the mean value, what happens? What's the difference?
xp of x of
Yes. Yeah. Now notice, even though in their very detail, fx and px don't mean the same thing. Yeah. This is exact probability. This is relative likelihood. But notice how similar. That's what I meant when I said a proxy. Yeah. So fx is going to behave as a proxy of the discrete case. It is going to sit in for that for all our calculations later. And this one a bit hard to swallow, but probability x equals a 0, and here probability x equals a is, yeah, this is where the difference is, and then we started with that, we have discussed it before, and next time we will go from one random variable to two random variables. Before this we have gone to from one event to two events. Remember, probability A union B, A intersection B, A given B. Yeah, but we were restricting ourselves formally to variables. Yeah, we're just making up events, and now we will do that, some of that with random variables, and it will lead to कौन सा function आता है नया? PDF हो गया. Yeah, we already have it in both cases. We have
Variance.
the CDF. Which one?
variance.
Variance, so you still have it in single variable. Yeah. Variance is x minus mean of x squared. This thing, yeah, you still have covariance आ जाता है वो
Yes, sir.
moments में, yeah. But in terms of the functions, not the not the information derived from the functions. Yeah, moments are the informations you derive from those functions. Yeah? But the function itself एक नया आ जाता है, बल्कि दो आ जाते हैं. Joint probability density function or marginal. Yeah. So how is marginal related to this guy? How is joint? How do these show up in the joint PDF? Yeah. So we have to lock all of that in the next lecture. Yeah. Yes, Sara, once we are done with all of these, you will be ready to work with random processes. Okay. Questions? फिलहाल नहीं है, तो बंद कर दीजिए. 1 hour complete हो गया.